Hi there, and welcome to the fourth lesson on the topic and chapter of trigonometric identities and equations. The main part of this lesson is looking at the idea of using simple substitutions to help us solve trig equations. And so the warm-up is going to help to get you used to this idea. So the warm-up questions here, especially questions 1 and 2, you might think seem particularly easy. And the point of these isn't so much to solve them, but to get you thinking about how question 1 relates to question 2, which I'll show you in a moment. So have a go at these warm-up questions as ever. Pause the video first and then press play just to check that you've got the solutions to these warm-up questions correct. So attempt them now, and then we'll have a look together at question 1. So question 1, use your calculator to solve the following equations where big X is some acute angle. So first of all, we have sine big X equals 0.5. So let's get our calculator ready here. So simply just shift sine and then 0.5. This will tell us the principal value of big X. And so here we can see that X would have to be equal to 30 degrees. So simple as that, X equals 30. Same idea for part B. Solve cos of big X equals root 2 over 2. So for this one, we're going to do shift cos, brackets, root 2 over 2, and you should find that this comes out to be the exact value of 45. So for B, X equals 45. And for C, tan big X equals root 3. So try this on your calculator if you're not sure what this is. It's one of these exact trig values. It's going to be 60 degrees. But shift tan of root 3, we'll verify that for you. So as you can see here, whoops, put the bracket in the wrong place. There we go. It's going to come out to be 60 degrees. So big X equals 60. And that's literally all there is for question 1. We can now have a look and think about warm-up question 2. Question 2 is where you might be thinking, well, what on earth is the point of this? Because it seems just so easy. I'm going to explain the point of question 2 is in just a moment after we've done it. So first of all, I know you can solve these. Theta minus 40 equals 30. Obviously, it stands to reason that theta is just going to be 30 plus 40, which is 70. If 2 theta is 45, we just divide by 2, so theta equals 22.5. And part C, if 3 theta was 60, divide by 3, theta must be 20. Dead easy. You might be thinking, well, what's the point of that question? The point is for D, E and F. So for D, E and F, it asks us to solve for theta, where big X is between 0 and 90 degrees. So just to remind you of what I meant by big X, here's what we had from part 1. So we had sine big X is 0.5, we worked out that X was 30. So for part A, we're wanting sine of something to be equal to 0.5, and so what we're actually doing here is we're substituting theta minus 40 with big X. Because this just looks unsightly and just looks and is more complicated to deal with. And so if we have a trig function with something awkward inside, we can replace the awkward thing for just simply big X and solve for just for one letter where big X is whatever it needs to be. In this case, big X was theta minus 40. And so for D, we had that sine big X is 0.5. We've had that X was 30 degrees, where X was theta minus 40. So therefore we can make theta the subject by just adding on 40 to whatever X is. So theta is 30 plus 40, which is 70 degrees. That's why I just mentioned big X here once again. For E, cos 2 theta equals root 2 over 2. So 2 theta, it's hard enough solving what cos theta is if you're not sure. So rather than saying it's 2 theta, we can replace the 2 theta with big X. And so just as before we had big X equals 30, for part B, our big X needs to be 45 degrees. And again, in this case, we can say big X just equals 2 theta. And so for E, our big X needs to be 45 degrees, where in this case, our big X, we're just calling that to be 2 theta. So therefore, we can get theta in terms of X by just doing X divided by 2. So theta equals X divided by 2. So 45 divided by 2, like we did for part B, theta would need to be 22.5 degrees. Same for F. And so for F, we can just call this tan of big X equals root 3, like we did for question 1. So if I just replace 3 theta and think of that as big X, we can see that big X would just need to be 60 degrees, where of course big X equals 3 theta. So if we write this down here, we can just say, well, X needs to be 60, where we're calling X equal to 3 theta. So just switching 3 theta with X, like so. And so then rearranging this again to get theta in terms of X, in our case here, theta is just going to be X divided by 3. So the value of X in between 0 and 90 needed to be 60. So 60 divided by 3, the corresponding value of theta we need is 20 degrees. And this is going to be the crux of this lesson. If we've got sine, cos or tan of some compound function, for example theta minus 40 or a 2 theta, or maybe even something like 2 theta plus 70, we just replace the awkward stuff with a big X, solve what we need big X to be, then after we've solved for big X, we then go back and think about what big X was in the first place to get the value of the variable we actually wanted to start with. Question 3. Write the equation 3 cos theta equals 4 sin theta in the form tan theta equals k, where k is some constant to be found. So what we can do here is just, first of all, just rewrite this as 3 cos theta equals 4 sin theta. If we now divide both sides of this equation by cos theta, we would get 3 equals 4 sin theta over cos theta. Now I'm going to put the cos theta only over the sin theta. We then need to remember one of the identities from the previous 2 lessons. So what is sine over cos? Well, you need to remember now that sine over cos is one and the same thing as tan theta. Sine over cos equals tan. That's a trig identity you need to have strongly ingrained in your minds. So now if we just rewrite this with tan theta on the left hand side, we can see that 4 lots of tan theta, where I'm just switching sine over cos with tan theta, 4 tan theta equals 3. Therefore divide both sides by 4, we get that tan theta must equal 3 over 4. So in other words, our value of k we're wanting is 3/4. Question 4. Factorise the following expression, 2y squared plus y minus 1. So I'm going to show you how to do this using the AC method. So if we multiply the 2 by the minus 1, we get minus 2. So we're wanting 2 values, 2 integers, that is, that multiply to minus 2, but add together to make positive 1. And those values are going to be positive 2 and minus 1. So we can split the plus 1y into a positive 2y into minus 1y. So then this bit here will factorise into 2y brackets y plus 1. The last two terms have a common factor of minus 1, so we can put a minus 1 on the outside of a bracket, and on the inside y plus 1. The 2y and the minus 1 can then go inside their own bracket. So we have 2y minus 1 brackets y plus 1. And that concludes our 4 warm-up questions, so we can have a look at solving some harder trig equations using this idea of substitution which I've talked about. Now we have 3 worked examples before you try some of these questions yourselves. These 3 examples are based on the warm-up questions, but I'm going to just start them from scratch, assuming that the warm-up was never done, just so you can see clearly from start to finish how these can be tackled without any reliance to the warm-up itself. So first of all, we're solving the equation sine theta minus 40 degrees equals 0.5 for theta from 0 to 360. Like I mentioned before, because this is a trig equation to solve, just do a cast diagram almost automatically without even thinking about it. So here's one here. So what I'm going to suggest is we just take this theta minus 40 and rewrite it simply as sine big X. So what I'm going to say here is let big X equal theta minus 40. Now because we're changing the variable from theta minus 40 to this x, this is also going to affect the limits of what we're searching for. We wanted theta to be between 0 and 360. Because x is whatever theta is but 40 less each and every time, we just subtract 40 from the lower limit and the upper limit of the range. So we want our x to be from 0 minus 40, which is minus 40, all the way up to 360 minus 40, which is 320. And just a reminder that theta in terms of x, if I add 40 to both sides, it's easy to see that theta is just whatever we work out x to be plus 40. So I'm going to put this in a bubble and just think about that in the back of my mind for now. So I'm going to rewrite this sine of theta minus 40 as sine big X equals 0.5, where, like I say, I've just swapped out 0 minus 40 and replaced it with big X. So using the calculator to work out what big X needs to be, we can get the principal value by just pressing shift sine minus 1 of 0.5, and we get 30. So the principal value like I've just done there, x equals sine minus 1, 0.5, and we got 30 degrees. So using this cast diagram to help us, like I said before, just draw a big X through the origin. And this is a cast diagram for big X. Okay, so this is based on big X. I'm just going to write this here, just so there's no confusion. I'm not talking about theta here. I'm talking about big X. So one value of big X which would work is 30 degrees. And sine big X is positive 0.5. So think about where the sine function would give us a positive value. The A quadrant is where all of sine, cosine and tangent are positive, so we're interested in this one here, which is 30 degrees. We're also interested in the S quadrant where sine is positive as well. And so the values of big X that interest us are indeed the principal value, which is 30, but also we're interested in this one over here. Now we've worked out the acute angles in between these lines are all 30. So therefore, it's fairly plain to see This angle I've just done in red for this quadrant will be almost 180, but just minus 30. So this one will be 180 minus 30, which is 150. So therefore, big X would need to be either 30 degrees or 150 degrees. But if we read the question carefully and just remind ourselves, we're interested in theta to answer this question, not big X. And so swapping X with theta finally, and reminding ourselves that theta is X plus 40. We just add 40 to each one of these. And so theta is either 70 degrees or 190 degrees. And before you finish, just make sure these are all the values in the range. We want theta to be between 0 and 360. And so these will repeat in intervals of 360. So 70 plus 360 and this plus 360 will be too big. Likewise, anything else, if we subtract 360 from these, will be too small. And so that's all the values there are to find. Question 2. Again, we're solving a trig equation, so just automatically do a cast diagram. And here, it's not just cos of theta or cos of x, it's a compound function, if you like. It's cos of something more complicated. So in this case, let's just call our big X as 2 theta. And so how this is going to change the limits, because x is double what theta needs to be, we double these limits on the range of theta. And so what that means is our big X is going to range from 0 times 2, which is obviously still 0, but it's going to go all the way up to 360 multiplied by 2, which is going to go up to 720. And of course, if X is 2 theta, it's just worth noting when we go back to thinking about what theta needs to be, that theta must be whatever X is divided by 2. So again, I'm just going to leave this here for later. So again, if I just make this switch and call this, oops, not 2 theta, but if I just call this here big X, we can now simplify this equation. So instead of thinking of it as 2 cos 2 theta, I'm going to think of it now as 2 cos big X equals root 2. So dividing both sides by 2, we see that cos x must be root 2 over 2. So now we can work out the principal value of what big X needs to be. So we just do cos minus 1 root 2 over 2. So shift cos minus 1 root 2 over 2, and we get 45 degrees. So we can add this to our cast diagram and consider what other options we may have for what theta eventually will be, but first of all, what x needs to be. So again, just like I've said before, we're considering what x is here, not theta right now. So this is for x. And so when x is 45 degrees, that works. So we worked out what this acute angle needs to be. Needs to be 45. And more than that, we can see here that the cosine function is a positive value. It needs to be positive root 2 over 2. So which quadrants are we interested in where the cosine is positive? Well, cosine is positive in the A quadrant because all of the main trig functions are positive here. So I'm going to highlight this one. And cosine is also positive in the C quadrant down here. And so in the range of 0 to 720, one value we've got for x, which is 45 degrees, so we can add this down straight away. So therefore we can say x could be 45 degrees. Or what we could do is go for this one down here. Now we're wanting x to be positive, so rather than going down here and making a negative angle, we go anti-clockwise from 0, 45, 90, 135, 180, 270, all the way around to here. And so measured anti-clockwise, this one will be 360 minus 45, which should be 315. So this one here is at 45. This one down here is an angle of 315. So x is 45 degrees, or could be 315 degrees. Now normally we might stop, because usually we want a range between 0 and 360, and the big mistake here is to stop. But actually, just remember, we're not talking about theta currently, we're talking about x, which needs to range from 0 to 720 before we consider what theta needs to be. So we take these values between 0 and 360 and add 360 onto each, remembering that cosine is periodic and repeats every 360 degrees. So if we add 360 to 45, we then get 405, and add 360 onto 315, we get 675. Now we don't keep going, because if we add 360 onto 405, we get 765, which is outside the range, because 720 is our maximum. So these are the four values we need, so we can stop. But of course, we want it in terms of theta. And remember, theta is x divided by 2. So all of these valid values of big X we found, we simply just half them now to get the values of theta which are required. So 45 divided by 2 is 22.5. 315 divided by 2 is 157.5. And again, please do use your calculator for this. 405 divided by 2 is 202.5. And lastly, 675 divided by 2 is 337.5 degrees. And that's all of them. Lastly, question 3, we're going to solve tan of 3 theta equals root 3, for theta being between 0 and 360. So once again, you might have guessed this, cast diagram straight away. And now, of course, we make a substitution for this 3 theta. We're going to let this be called x. So once again, make a substitution and let x equal 3 theta. And so our range of theta we wanted was between 0 and 360. If x is triple of what theta is allowed to be, we triple these limits here. So our limits for big X are 0 multiplied by 3, which is still 0, and 360 multiplied by 3, which is going to be 1080. And just to remind ourselves, theta in terms of x, theta is just going to be whatever we find for x divided by 3. So we're wanting to solve tan big X equals root 3, where of course, like I've said before, we've swapped 3 theta with big X just to make it read simpler and be simpler, in fact, to solve. So we can find the principal value of x by just doing inverse tan of root 3. And if we did tan minus 1 of root 3, I invite you to try this on a calculator yourselves. This is one of these exact trig ratios. You'd find it to be 60 degrees. And this principal value is within the range, and so this is one value of x we're going to include. So we take our cast diagram, draw a big fat X centered on the origin on it, and because we found a acute angle, which is valid, 60 degrees, we just add on 60, like so, in each of these quadrants where 60 is the acute angle made with the x-axis. Yet again, this tan function needs to be positive because we've got positive root 3. So whereabouts is the tan function going to be positive? Well, in the A quadrant, all of sin, cos and tan are positive, so we're going to consider this bit here. And also the T quadrant is where the tangent function is going to be positive. And so 60 degrees is relating to this one here. This angle here, measured anti-clockwise from the positive x-axis, that's 90, that's 180, 180 plus this 60. This is going to correspond to an angle of 240 degrees. So, therefore, in the range of 0 to 360, the values of x we're interested in are 60 and 240. But of course, our range of x is going all the way up to 1080. And so because the tan function is periodic and repeats actually every 180 degrees, we just simply keep adding lots of 180 onto these values. 60 plus 240 is, 60 plus 180 is 240. So we're just going to go up in 180 degree increments. Another way of doing it, if you wanted to, just take each of these and add 360 degrees onto both and do it that way. So for example, 60 plus 360, that's going to be 420. This one plus 360 is 600. Keep going. This one plus 360 is going to be 780. That one plus 360 is going to be 960. Now, if we added any more on, we'd be outside of the range 1080. So this is all the values which will work. And again, if you look at this sequence, it's going up in 180 degree lots. This is because on the cast diagram, the regions where tan is positive makes a straight line, and angles on a straight line add up to 180. So we're going around in 180 degree swivels, 180, 180, 180, 180, again and again. But of course, just remember, we want theta, not x. So our final answer, to go from x to theta, we take our x's and divide each of them by 3. And so 60 divided by 3 is 20, 240 divided by 3 is 80, and so on for each of the values above. And again, use a calculator to make sure you don't make any silly mistakes like I'm quite likely to make. But don't worry, I've checked these beforehand, so I can assure you I'm not making these mistakes right now, thankfully. And that one is going to be 320 degrees. And so that concludes the worked examples. But before I finish, I have mentioned Desmos before. Some teachers really love Desmos, some teachers more GeoGebra, some teachers don't really care and love both. Just to show you how you could have used GeoGebra to get all of these solutions. Here's a screenshot I've taken from desmos.com. And I can also recommend the app, which is available for Android and iPhone. So you could have tried tan 3x equals y to get these tan function lines drawn in. I'd say tan lines, but we don't really live in a country which is conducive to getting nice tans. And then you could have also plotted where y equals a constant root 3. Where they cross correlates to the solutions here. So as you can see, 20, 80, 140, 200, 260 and 320. So this plotting software, Desmos or indeed GeoGebra, is very powerful and just makes sure that you're not missing any, because a calculator is only useful to some extent for these questions. It will only find the principal values. It won't be helpful for finding values outside of the principal ranges. So just bear that in mind. Have a play around with Desmos.com if you get the time. Anyway, over to you guys now. So page 218, exercise 10e in the book. Try all the questions, it can't do you any harm. So keep working on those, and please do subscribe to the channel if you can. That'd be very nice of you. Thanks again for listening and getting to the end of the video. Take care, and I'll see you all soon. Bye for now.